Hey everybody. So we are going to take a look at building a confidence interval in this video. So it's a bit of a process, and I'm going to try to explain each step as we go, but then at the end I'm going to summarize exactly how we construct these things in a very formulaic way, right? So the goal here is, if we can understand as many of the steps along the way, but it might not quite happen after one video, right? It might not quite happen after working several problems. But eventually we'll get there. In the meantime, we'll have a way to compute them that's pretty straightforward, and we'll slowly build our understanding as we move, okay? So here's the example I want to do. Right, so remember what we're doing with confidence intervals is we're trying to estimate some population parameter, and we're gonna stick to confidence intervals right now, where we're estimating the mean of a population. So suppose we were going to do a study of human body temperature. Okay, so we want to estimate body temp for some population, right? So maybe it's a population of people that for some reason we believe maybe has a different body temperature, something like that, like slightly different than everybody else. Who knows? We're trying to estimate this human, estimate body, oops, I forgot the word temp in here, human body temperature for a population of humans. Okay, so in other words, there is a variable I'll call X is the body temperature for humans in the population that we're talking about, right? And what we're trying to find is the mean of this, right? Now, let's assume that we know humans in general have a standard deviation for body temperature of 0.30 degrees Fahrenheit, okay? So we already know that information somehow. So here's the idea. We're going to construct what we're going to call a 95% confidence interval. Okay, so we'll explain what that 95% means in just a moment. So imagine you're a researcher trying to do this. One thing you might do is sample 106 humans in this population for their temperature, right? And take the average, right? Find an average body temperature, right? Well, when we do that, let's put that up here. Let's say, suppose we sample 106 humans and we find an average temperature or a mean temperature among these 106 of 98.44 degrees Fahrenheit. Okay? Now, what we've done is we've created a new random variable called the mean body temp with n of 106, right? So this new variable is related to the original one. The original one is body temperatures for humans in this population. We've now taken the sample mean body temperature. Maybe I'll put sample in here. For sample sizes n 106, right? What do we know about x bar? We know, according to the central limit theorem, that it is normally distributed and that its mean, whatever it is, we don't know what it is, it's the same as the one we're looking for, right? Remember, we're looking for the mean of x, but we know the mean of x is the same as the mean of x bar. We also know that the standard deviation is related to the standard deviation of x by the formula, the standard deviation divided by the square root of the sample size, right? So in this case, that works out to be We still don't know the mean, but if you work out this computation, I have it here. The standard deviation is 0.029. Okay, this is still in degrees Fahrenheit. Okay, so we went out and sampled 106 humans, and we found that their mean temperature was 98.44 degrees Fahrenheit. Okay, so this little x bar, remember, is a single data point in the distribution capital X bar. Let's try to draw a picture of the situation. Here's my data values are in the horizontal axis. So data values for capital X bar. I'll try my best to draw, let's use another color. Let's try red. A normal distribution. All right, so there's our normal distribution. We know whatever the mean is, right, that's the middle of our normal distribution. That's the value we're trying to estimate. We went out and sampled 106 humans. We got one data value in this distribution, right? Remember, all the data values for capital X bar are along this horizontal axis. We went out and got one of them. We got 98.44 degrees Fahrenheit. We might go out again and sample 106 humans and get 98.26 degrees Fahrenheit mean temperature. And then we do it again and we get 97.98 degrees Fahrenheit, 98.75 degrees Fahrenheit, right? We could go out and do all these samples and we'll get different values along here. These are all the data points in this distribution. So we don't know exactly where our data point lives, right? I don't know if it's above or below the actual mean. So it could be anywhere in here. Here's what we do know, and here's where the 95% confidence interval comes in. We can find, or what we're going to try to find, are two values. All right, so my picture's not great here. This graph should be more symmetric, where they're going to be some distance above and below the mean. This distance is what we're going to call our margin of error, or I'll just call it E for now. Sometimes people call it EBM, error bound on the mean. E is easier to write in a small space. What we and that's how far they are from the mean. Some distance below and some distance above. And we want to find these two values so that between them we find an area of 0.95. In other words, all the values between these two places I've marked here, whatever they are, right? 95% of all sample means should land between these two values. That's the idea. We just did a sample mean. In other words, if we did this experiment 100 times, we would expect 95% of the time, 95 out of 100 times, our sample to be somewhere between these two values, okay? Now, we don't know what mu x is, so we don't know exactly, we won't be able to get these values exactly, but we'll do some trickery in a moment, okay? So let's try to compute this error, all right? So this 95% is what we call C. That's the confidence level, or CL sometimes. So CL is our confidence level. We'll also have another variable we sometimes use called alpha, which is just going to be 1 minus CL. So in this case, it is 0.95 is our confidence level. 0.05 is alpha. Alpha is just the amount of area left in the tails, right? If there's 95% here, there's 5% left in these two tails, which means 2.5% in each of them, right? So that number is the amount of area down here, okay? So here's what we're gonna do. We're gonna go to our standard normal distribution, the one with a mean of 0 and a standard deviation of 1. And we're going to find two z-scores that have 95% of the data between them, okay? And sometimes these z-scores are called, this one would be z with a subscript alpha over 2, and this one is negative z with a subscript alpha over 2. Different authors note these different ways. It's just a way of saying this is the z-score with alpha over 2 area above it, that 0.025. This is the one with alpha over 2 area below it, that 0.025, okay? We're going to find these z-scores to find how many standard deviations we have to move from the mean to get 95% of the data. And if once we know how many standard deviations we have to move, then we can translate the number of standard deviations times the size of a standard deviation. That tells us how far we should move from the mean to capture 95% of the data. In other words, that's our error. Well, what the number of standard deviations is just this alpha over 2, and the size of the standard deviation is just our standard deviation. So it will be for this, the data values for x bar, that's going to be the standard deviation of x divided by the square root of n. And this is always going to be our formula for the error. All right, let's go through this process. So the first thing I want to do, let's jump now to a calculator. Let me see if I can shrink it enough that we can see it below all this writing. I want to keep this writing up for a bit. So notice I've already put in, I want an area of 0.95 on my standard normal distribution. And what this has told me is that between a z-score of negative 1.96 and 1.96, we will find 95% of the area, right? Or area 0.95. In other words, this is telling me that z of alpha over 2 is equal to 1.96. Right? This will always be the case when we're doing a 95% confidence interval, right? And we will do 95% confidence intervals often. That's one of the common intervals to do. 90, 95, 98, 99, those are pretty common ones. And once you find the number for each one, the right z-score, it doesn't change because it only has to do with the standard normal distribution, okay? All right, so let's go back to our error computation. So we're almost there. Let's compute this error. So I now have z of alpha over 2. So the error is going to look like 1.96 times sigma x divided by the square root of n, but we already computed that over here, 0.029. And I get an error of 0.057. Okay, so let me try to explain again what this number is telling me. So let me move a couple of things around really quick. Oops. Whoops. All right, so I'm going to put these down here. Let's just get rid of this. Sorry, this is still learning. Okay, so we've got this formula for the error. I also want to keep that. This can go away. And then we've computed the error down here. All right, so now what is the meaning of this error? Okay, let's go back up to this picture above. So what we have determined is this is degrees Fahrenheit. Z-scores have no units, they're just numbers. This was their standard deviation in degrees Fahrenheit. What this number is telling us is that for the distribution X bar, 95% of the data lives between this error above the mean. I'll just have to write it. All right, so what this is telling me is if I take the mean and subtract this error from it, and I take the mean and add this error to it, we don't know what the mean is. So I don't know what these numbers are exactly, but I do know that if I go this far below and this far above the mean, that between those two numbers, I get 95% of the data. So between ux minus 0.057 and mu x plus 0.057, we find 0.95 of all sample means. Right? So we expect that this X bar that we took, it's not precisely accurate to say, but it's a reasonable way to think about it. It has a 95% chance of being between these two numbers, whatever they are. In other words, X bar, 98.44 degrees F, is within 0.057 degrees Fahrenheit of the mean, with 95% confidence. Okay. Well, if X bar, little x bar, is within 0.057 degrees Fahrenheit of the mean, that means the mean is within 0.057 degrees Fahrenheit of X bar. We can turn that around, right? If I'm within 2 feet of my brother must be within 2 feet of me. We can go in both directions. So in other words, we can say mu x is less than 0.057 degrees Fahrenheit from X bar, with 95% confidence. Well, what does that mean to be that close to X bar? It means we have an interval. We can take 98.44 degrees Fahrenheit minus 0.057 degrees Fahrenheit, and we can take 98.44 degrees Fahrenheit above 0.057 degrees Fahrenheit and create an interval. And if you do that computation, we get 98.38 degrees Fahrenheit and 98.50 degrees Fahrenheit. And we would say, this is our 95% confidence interval on the mean. Right? So with 95% confidence, we expect the mean to be between these two numbers, right? It's an interesting little bit of reasoning. We're expecting that this sample that we took is very close to the mean, which means that the mean must be very close to the sample. So we just kind of reverse that idea, right? If I told you I chose a number and it's within 2 units of the number 10, right? So it has to be, if I chose the number 8, if I chose the number 8 and I told you it was within 2 units of another number that we're looking for, right? Well, all the numbers that are within 2 units of my number are between 6 and 10. So I've taken my number and gone in 2 units in both directions to get an interval where that other number must exist. That's the idea that we're doing here. Okay, That's what a confidence interval is, right? This is one type. This was a, we were looking for the mean. We knew the standard deviation of the population. That's a little bit unrealistic, but it's a good place to start. We'll talk about how to do it when we don't have that standard deviation in later videos. Let me finish by summarizing this process. We'll do more examples in other videos, but I want to summarize it once. So let me clear this stuff. So given our general process is we want to find let me start over. Actually, I got a better way to say this. We're going to start, there's a random variable x, some random variable. We want mu x, and we know sigma x, okay? That's where we're starting. And then we create x bar, right, which is going to be normal with the same mean and a standard deviation equal to the square root of n. The original standard deviation divided by the square root of n, the sample size, okay? And we'll have an actual data value from capital X bar, a single sample mean, okay? So that's where the problems will usually start. That's the situation we're in. If you were a researcher, you'd actually have to go out and get this sample mean. You would have started with wanting some parameter like the mean and having some information like the standard deviation. You go out and get the sample. For the examples I do, we're not doing that part. We'll just be assuming somebody has done that research for us, and we've got to create the interval. Okay. Then we have to find. So this is all generally given. We're going to find the critical z values. That's what we call these sometimes, that I called z of alpha over 2, right? So all that means is if you have a standard normal distribution, the area between these two critical z values is the confidence level. We did a 95%, so it's 0.95. If you did a 90%, it'd be 0.90. And then in these tails, there's going to be alpha over 2. Alpha is 1 minus CL, so you divide it by 2. So using an inverse normal calculator, you can find the critical z value, right? We just usually look for this positive one. Okay. So once we have that, we compute the error bound on the mean. This is going to be this z of alpha over 2 times the standard deviation of our distribution of sample means, but that is just the standard deviation of the original that we know divided by the square root of n. Okay. And then from there, your interval is just x minus the error, x bar plus the error. Okay. That's what all of this boils down to, right? That's all of this boils down to. Sometimes people might write this like plus or minus the EBM, right? It's saying this value go that far above and below, right? That's what that notation means. Okay. That's it. We'll do some more videos with examples now that we've got this process, but that one takes you through the whole idea of this kind of confidence interval. All right. Thanks, everybody. I will see you next time.